The energy required to warm a continent or power a hospital's cancer ward doesn't come from the large-scale objects we see. To find that power, we have to look past the macroscopic world and into the smallest structures in the universe. In 1803, John Dalton proposed what we now call the billiard ball model. He imagined atoms as tiny, indestructible solid spheres that bounced off one another without ever breaking or changing their internal structure. That model was revised after the discovery of the electron. In 1904, J.J. Thomson proposed the plum pudding model, suggesting the atom was a sphere of positive charge, with negatively charged electrons scattered throughout it like fruit in a pudding. While both models were eventually replaced, they represent the first steps in a process of tearing apart our assumptions about the solid matter that makes up our world. In 1911, Ernest Rutherford tested Thomson's model by firing positively charged alpha particles at a microscopic sheet of gold foil. Based on the pudding model, he expected the particles to pass straight through the diffuse positive charge. Instead, some particles bounced straight back. Rutherford concluded that the atom is mostly empty space, with almost all of its mass concentrated in an unimaginably tiny, dense center called the nucleus. Niels Bohr refined this by proposing that electrons orbit the nucleus in specific fixed energy levels. This planetary model explained why atoms emit specific colors of light rather than a continuous rainbow. By the 1920s, Schrödinger and Heisenberg realized electrons don't travel in neat rings. Because of the uncertainty principle, we describe their positions as orbitals, 3D regions where there is a high probability of finding an electron, creating a cloud around the nucleus. This evolution of models reveals that the solid matter we experience is actually a vast expanse of empty space. The physical properties of our world are governed by the dense, high-energy nucleus at the center of that void. Packing positively charged protons into a space as small as a nucleus creates an immediate physical tension. Because like charges repel, the electrostatic force should cause these protons to push away from each other and destroy the atom. They stay together because of the strong nuclear force. It is the most powerful force in nature, acting as a high-strength glue that only works over incredibly short distances to bind protons and neutrons together. Measuring these particles reveals a strange property. An intact nucleus actually weighs less than its individual separated protons and neutrons. This missing mass was converted into binding energy, the energy required to hold the nucleus together against its own internal repulsion. This missing mass represents the structural energy of the atom. It functions as the primary fuel source for every star and every nuclear reactor. When an atom becomes too large, the strong nuclear force can no longer reach far enough to hold the distant particles together. This makes the nucleus unstable, leading it to shed mass and energy in a process known as radioactivity. Alpha radiation consists of heavy helium nuclei, stopped by a single sheet of paper. Beta radiation is composed of smaller, fast-moving electrons that penetrate paper but stop at aluminum. Gamma radiation is a high-energy electromagnetic wave, requiring thick lead to absorb. We measure the rate of this process using half-life. This is the constant time it takes for exactly half of a radioactive sample to decay, a rate that remains identical regardless of the sample's size or environment. Radioactive decay serves as nature's mechanism for restoring balance. By shedding excess mass and energy, an unstable nucleus eventually reaches a stable final state. We can trigger this artificially. In nuclear fission, a neutron strikes a heavy, unstable nucleus, forcing it to split. This releases massive heat and additional neutrons, which strike other atoms, creating a self-sustaining chain reaction used in commercial nuclear plants. Nuclear fusion works in reverse. By applying extreme heat and pressure, we force light nuclei to fuse into a heavier element. This process releases significantly more energy than fission and serves as the primary engine for the Sun and all other stars. Whether we split large atoms or fuse small ones, we are accessing the strong nuclear force to release energy millions of times more dense than any chemical combustion. These microscopic forces have direct macroscopic applications. In medicine, we use the penetrating power of gamma radiation to destroy cancer cells. keeping it safely contained within thick lead shielding until it is precisely targeted. In archaeology, the constant decay rate of carbon-14 acts as a geological clock. By measuring remaining isotopes, scientists accurately date artifacts and historical sites. For our global infrastructure, fission provides a high-density energy source. These reactors produce large-scale electrical power with a significantly smaller physical footprint than fossil fuels. The most significant application remains stellar fusion. It's the efficient mechanism that keeps the sun burning, providing heat and light that sustains all biological life. From treatment rooms in our hospitals to the power in our grids and the light from our stars, the visible world is a direct product of those invisible rules governing the dense nucleus of the atom. To explore more about the physics of our universe and access further educational resources, visit yaka.cc.